Good morning, ladies and gentlemen. Welcome to the fourth day of the conference. We'll start soon the session 11. The chair of this session 11 is Mohammad M. Akbar. I am requesting Professor Mohammad Akbar to proceed with the session. Thank you.
Hello everyone, good morning. We would be starting our session right now. The first person to speak, I have his name here, is Professor, wait a second. Yeah. Ulrike, that was cancelled, my bad. So Professor Adhikari, Narayan Prasad Adhikari. He'll be talking on protein-protein and protein-DNA interactions insight from silico study. Thank you.
Good morning. It's my pleasure to be here. I am thankful to organizer, especially Professor Kamrul Hassan, who invited me in this program. And today, I'm going to discuss about protein-protein interactions insight from in silico study. Actually, in this work, we try to sample difficult places of phase space by using different techniques, umbrella sampling. That's why it's somehow related to, it's related to StartMake, which was actually work of Bose, Bose. And further, I'm connected with Bose because not only as a physicist, but I have been teaching large number of physics students, graduate physics students at Tribhuvan University for the last 30 years and teaching StartMake. So that way, actually, I'm imparting what Bose gave to us to our youngsters. So in this talk, I will discuss about SARS-CoV-2 virus, understanding binding mechanism of COVID-19, human S2, umbrella sampling. So if we see recent data, there were 704 million people were actually affected by coronavirus and more than 7 million deaths across the globe. So seeing all those things, we wanted to understand why it's happening. What is the binding mechanism of this COVID virus to our human body? As a physicist, we try to understand those ideas. So this is this green one is our protein, our body's protein, human S2. That's what we call it. And this big part is spike protein. From this spike protein, what we do, only these binding sites we consider because it's really difficult to carry on molecular dynamic simulation of all this system. So this figure shows the receptor binding domain. This receptor binding domain is key part of virus. This virus proteins. This RBD or receptor binding domain is only this part. And this figure shows the RBD as a key part of virus located on its spike domain that allows it to dock to body receptors to gain entry into cells and lead to infection. Actually, this is the main culprit from this spike protein. And this is our human angiotensin converting enzyme 2, what we call it as HS2, SCE2, HS2. So this figure shows the binding of this SARS-CoV-2 protein receptor and this human S2. And we were one of the first people to identify how these bind together. And actually we identified 3 different binding regions between this human protein and this spike RBD parts. And there we can see that the after finding these 3 regions, especially in SARS-CoV and SARS-CoV-2, they are more or less the same. Only this in between part, this middle part is missing in the case of SAR-CoV. This is the simulation box which shows our system. This is RBD part and this HS2. This all the background, whatever you are seeing with red head and two small white tails, they are water molecules. So what we do, we carry on molecular dynamic simulations by taking all this huge system, and we consider different variants to understand binding mechanism, as well as this work actually help us to understand why some variants are quite severe and while some are not. And this wild type, beta variants, delta variants, mu variants, and Omicron, we carry on, we study all these five different types of systems in water for 100 nanoseconds molecular dynamic simulations, and total number of atoms are approximately 250,000. This is huge system. So actually we were interested because different time schedule variants of concern were declared by WHO. For example, wild type, when it came, it was already this concern or alarm across the globe. And then this beta was declared variants of concern in December 2020, delta in May 2021, mu August 2021, and Omicron November 2021. So what is this different variants? What happens? I just want to explain to our young students what are these different variants. So, for example, these amino acids were there in case of this spike protein in wild type or whatever it first came, and then this amino acid converts to this lysine, amino acid converts to ASN 417. So, a lot of structure changes in the case of beta, and glutamic acid 484 changes to lysine 484 and ASN 501 to tyrosine 501 and so on. In this way, when one amino acid converts to another one, there will be different variants, or this is what we call this mutation. Similarly, in case of delta, there are only two amino acids who are converting leucine to arginine and threonine to lysine. And in the case of mu, there were three mutations, arginine, glutamic acid, and ASN. And in Omicron, actually, there were 15 different mutations, or 15 different types of amino acids were converted to different others, one like this. I am not going to discuss all of them. Anyway, we can discuss anybody who is interested here. And first, our task is to understand whether all these variants of concern are stable or not. Of course, they were stable. They were attacking us. We were in pandemic all over the globe, but still, we wanted to test it from our simulation also. And this figure shows this is the virus and this is human protein. And when they bind together, we wanted to see whether it collapses or it remains stable. This figure presents root mean square deviation versus time. As I already mentioned, time is 100 nanoseconds in our case. So this shows different types of variants are stable by time. This means all these variants, especially this mu, delta, beta, Omicron, and wild type, all are stable, seen in our lab also. And we wanted to understand the major binding factors in protein-protein interactions. They are hydrogen bonds, salt bridge interaction, hydrophobic interactions, non-bonded interactions, and binding free energy by umbrella sampling. This figure shows the number of hydrogen bonds versus time. Number of hydrogen bonds, actually what happens in such systems, since the system is dynamic, number of hydrogen bonds keeps on changing. So number of hydrogen bonds actually keeps on changing in all the cases. What we do, this number of hydrogen bonds is not changing drastically, I mean monotonically, nor decreasing nor increasing. This means there are certain average number of hydrogen bonds. That's what we can estimate our simulation. And from this figure, we can see that this red one, for delta 1, number of hydrogen bond on the average is highest one. And this is mu1, green one is beta, and this pink one, merino one is for this omicron. So for omicron, number of hydrogen bonds is small, but in the case of delta, number of hydrogen bonds is highest. This table again presents the same number, same figure. Wild type has on the average 6.5 number of hydrogen bonds. Beta type has 5.3 hydrogen bonds on the average. Delta has 7 and mu 5.4, omicron 4.7. So this means omicron has least number of hydrogen bonds, whereas delta has highest number of hydrogen bonds. So number of hydrogen bonds actually key factor to bind in biomolecules. So this table shows actually hydrogen bonds occupancy, which have been presented by here bar diagram. Here this figure presents again this hydrogen bond occupancy. Number of hydrogen bond only doesn't matter. Actually what matters is hydrogen bond occupancy, or how many times the hydrogen bond attached or hydrogen bond formed in our system. So this blue one is for wild type, this red one is again for delta, and then this green one beta, and so on. From this bar diagram, what we can see, in the first case, this green one is missing. Means in case of beta, first hydrogen bond misses, or there will not be first hydrogen bond. Then we try to understand what is the implication of this, whereas in the case of first hydrogen bond in our picture, this delta has highest occupancy. So we again try to understand what are the implications of this having highest occupancy of delta variants. And all other variants are on the average decreasing. And in case of omicron, number of hydrogen bonds are too many. Because if you remember, there were 15 different mutations going on in case of omicron. So what happened after then, but the strength of hydrogen bond is quite less, because occupancy is less than 20% in most of the cases. So we again further try to understand hydrogen bonds in beta mutation. As I already mentioned, in this case, in first case, this hydrogen bond misses, and other case there are some hydrogen bonds. And we wanted to understand why that hydrogen bond was missing in case of first hydrogen bond was missing in case of beta variants. If we see, actually in this figure we highlighted different amino acids what went mutation. For example, this lysine 417 goes to aspartic acid 430. They were forming this hydrogen bond in case of wild type. We can see that the distance between this and this is quite close in comparison to after distance. For example, this lysine converted to ASN, which is a bit further from this one, in this green one. So this shows that this and this is highly unlikely to form hydrogen bonds, or they are already far apart not to form hydrogen bonds. That's why this hydrogen bond, one main crucial hydrogen bond in beta was missing. Similarly, in case of delta, if we compare delta variants and wild type, then this red one is for delta, hydrogen bond occupancy percentage, whereas for this blue one is for wild type. We can see that in case of delta, hydrogen bond occupancy is higher in all the case of this simulation, in all the case of hydrogen bonds. So this further showed the same figure for mu type of variants. And in mu type, there is one having hydrogen bond occupancy approximately 90%, and some others are having quite less percentage. And in Omicron, as I already mentioned, first hydrogen bond is misses, but in all other cases, there are too many hydrogen bonds, one thing. Second thing, hydrogen bond occupancy is quite less in comparison to this stronger one, which are having approximately 90%. So actually what happens from our simulations, we can conclude that these hydrogen bonds actually, even though number is high, strength is quite low. So in case of Omicron, we wanted to understand why this hydrogen bond, first one is missing. That we can see from this figure again, like in the case of beta. This figure shows in case of wild type, this lysine 417 and aspartic acid 30 are quite closer. But in case of wild type, however, in case of Omicron, they are farther apart. Same type of idea applies here also in case of Omicron. Then we wanted to understand why this wild type Omicron has higher number of hydrogen bonds than wild type. This figure presents actually another such situation in which this Omicron, when this wild type to Omicron converts this amino acid, this comes much closer to this other sites one, so that it forms again hydrogen bond. This figure shows the electrostatic interactions in different variants. This electrostatic interaction, this figure, this y-axis is in negative and this axis is time in nanoseconds. This means again highest strength of electrostatic interaction can be seen in case of delta, because delta is much stronger, approximately sometimes approximately 300 kilocalorie per mole also. And lowest one is beta, this which is presented by green one, in which this strength is approximately, this energy is approximately 100 kilocalorie per mole. And the question comes, why we get these electrostatic interactions? Actually, when these mutations happens or not, in many cases, these amino acids carry, some amino acids carry charge. In those cases, because of those charges, we get these electrostatic interactions. And further, we know that the system is studied underwater. That means again, this electrostatic interactions is stronger. For example, this table presents arginine, lysine, and his, which carry positive charge, whereas the glutamic acid and aspartic acid carry negative charge. Then comes this out of non-bonded interactions. We actually try to understand van der Waals and electrostatic interactions. In case of van der Waals interactions, this one is this Omicron variants carries much less in comparison to actually beta 1. In beta, hydrogen bond electrostatics, they were less. However, van der Waals is highest one. But van der Waals, we know that it's weak. So anyway, whatever is dominating in electrostatics, that will still dominate in total. So this figure presents this non-bonded interactions in different variants. This green one is for beta 1 and this red one is for delta. And we can see from this table that this delta has highest value of non-bonded interactions. It is approximately 260 kilocalorie per mole, whereas this beta has least one, which has 165 kilocalorie per mole. And another interactions, what plays crucial role in binding of these biomolecules is salt bridge interactions. Salt bridge interaction in proteins is actually a relatively weak ionic bond between positive and negative charge sites in proteins. In this case, this figure presents this SARS-CoV-2 for SARS-CoV-2 by this red one and SARS-CoV for this blue one. In case of SARS-CoV-2, the distance is quite less in comparison to SARS-CoV-1. That's why salt-bridge interactions is much stronger in case of SARS-CoV-2 in comparison to SARS-CoV. So the reason behind it is, I mean, both of these lysine and aspartic acid, they have positive and negative charge. That's why these salt-bridge interactions come into play, which is actually main mutation when we come from SARS-CoV to SARS-CoV-2. So salt-bridge interactions were observed in case of wild type, delta, and mu, and all of them are well below 5 angstrom distances. This means they are quite strong salt-bridge interactions. Another quantity what characterizes this, which helps to understand this binding of different proteins is solvent accessible surface area, what we call SASA in shortcut. This figure shows the SASA for RBD as a function of time again for 100 nanoseconds. Approximately, I mean, delta has highest one, and this beta has lowest one. All have in between delta and beta variants, and this is approximately 11,000 angstrom square. Similarly, SASA for HS2 for different variants, we can see they are approximately 30,000 or 28,000 angstrom square. And SASA for RBD and HS2, this we can see, they are approximately 38,000 in total. Means there is some difference between individual and this buried one. This happens because when this RBD and HS2 interact, one is buried under this other one. That's why the total surface area decreases in case of binding. This means whatever strength it decreases, that actually contributes higher binding energy. So that's why this binding energy can be related with this net contact surface area also. And net contact surface area in case of delta is highest. It is approximately 900 angstrom square. And wild type also has highest similar type. And this Omicron, beta, they have less amount of this contact area. This means both the proteins are relatively separated in comparison to this one. And this figure shows the hydrophobic interaction. We know that hydrophobic interaction again plays crucial role in case of binding protein-protein or in any biomolecular interactions. This one is RBD, this red one is RBD, blue one is for human protein. And we can see that from this RBD, some amino acids, actually F486, come and inserts into the hydrophobic group created by this F28, L29, and M82 in HS2, in this region actually. So this is again presented by the same information, somehow different ways. So after trying to understand all these binding ways, hydrophobic, hydrogen bond, electrostatic interactions, and so on, we wanted to find out what is the binding free energy of different variants. This is what we wanted to do it by umbrella sampling. Umbrella sampling is the way of sampling phase points when we do simulations in which unreachable points are somehow we get by biased, and then that biased part will be corrected later on. So it is useful to sample easily unreachable phase points. We need to use first biasing potential. In case of present study, we use harmonic 1 to sample such points in phase space. Then to estimate the binding free energy, we apply WHAM, a weighted histogram analysis method. This is well established method. We consider this force constant to be 1.5 kilocalorie per mole square, and equilibration time we took 5 nanoseconds. In this case, 1 femtoseconds per step, that's what we did. And production run in NPT ensemble, I mean keeping pressure constant, we carried out for 10 nanoseconds. For production run, 2 femtoseconds per steps. So this table represents these different systems what we carried out for this umbrella sampling. All these, they were done for 10 nanoseconds only. So this figure shows what we do. Actually, we do in umbrella sampling. We first consider two proteins in water. Of course, water environment is there, which is not shown in the figure. And then we just, from center of mass of this, fixing this, we just pull center of mass of this whole protein to this side, say right side. And then by 1 angstrom, and then we again equilibrate the system, and we find out the binding free energy. Then what we do, we again pull by 1 angstrom. Again, we equilibrate the system, and then we find the binding free energy. Again, we pull by 1 angstrom. This center of mass distances keeps on increasing, and finally they are separated. So to make sure that our system is well equilibrated, this figure shows this distributions versus this center of mass distance, and what is the main criteria to satisfy this umbrella sampling is there should be enough overlap between all these umbrellas look like distributions, and from this figure it is seen that they are more or less overlap quite well. And this figure presents this umbrella sampling binding free energy for wild type and beta type, and this beta is green one and wild type blue one as usual color, and this difference is 0.32 kilocalorie per mole. This difference we obtained from this minima of these both of these curves. Similarly, this figure presents the difference of binding free energy obtained from umbrella sampling in case of delta variants, and it is 0.54 kilocalorie per mole. And this figure shows the same information for Omicron, and here it is difference is 1.27 kilocalorie per mole. And finally, we compared our data, even though they are already published in PCCP, with this previously published data by Kim et al. And the point what these Kim et al. Did is they actually carried on SMD, and they calculate this force, where this force is maxima, this minima has to be there, and within error bar of our calculations, this position of this maxima and this minima agree very well, and they have carried out this simulation for epsilon and kappa and others one also, which the work we are still carrying on after publishing all this work also. So one of the ways to get binding free energy is MMGBSA, what we call molecular mechanics generalized bond surface area method. And in this method, we consider all the energy terms and entropy contributions. We estimate, in our case also, we estimate this MMGBSA binding free energy, which is given by all these interactions terms, bonding, electrostatics, van der Waals, from polarization and non-polar term, and then this entropic term we need to subtract. So from MMGBSA, the estimated values are approximately 40 kilocalorie per mole within error bar of 8 to 9 kilocalorie per mole. And finally, the conclusions. Changes in hydrogen bonds due to mutations in different variants like beta, delta, mu, and omicron have been studied. Similarly, changes in salt bridge, hydrophobic, van der Waals, electrostatic interactions have been studied due to mutations. Our results show that delta variants have highest binding free energy. This helps somehow to understand why delta variants was quite severe in our region, especially India, Nepal, like this. And our umbrella sampling results agree with previously reported results by SMD. Acknowledge goes to all these peoples, my students who worked. Thank you very much for kind attention. Thank you.
Questions for Dr. Adhikari?
In the slide number 11,
Yeah.
could you please go there? there is a significant difference in the ion ratio
Yeah.
for mu variant.
Yeah.
I'm just curious to know what is the reason behind it.
So what happens when this mutation happens? When this mutation happens, this sometimes there will be this residue. I mean, these amino acids carry some charges, some losage. That's what we are discussing here. Okay. In some cases, the answer is that in some cases, there will be charged amino acids. In some cases, there are not. Not all the amino acids carry charge. I mean, for example, sorry, I had here. Number of hydrogen bonds in electrostatic interactions, hydrogen bonds. Yeah. So some amino acids carry positive charge, some carry negative charge. If there will be positive and negative charge, this electrostatic interactions increases. And if the mutation happens, for example, this lysine converts to something else which doesn't carry charge, then the lysine has positive charge. Wild type case, to neutralize the system, we need to add less amount of charge.
Any further questions? Okay, if there is no further questions, let's give a big hand to Dr. Adhikari. Thank you.
Okay, thank you.
The next session speaker is Professor Dr. Mohammad Nurul Huda from University of Texas at Arlington. He is going to talk to us about photoexcited electrons transport in metal oxides, Polaron formation.
Okay. Your pointer. Yes. Thank you. Good. I guess it's still good morning. So I will be presenting my work, rather my group's work, on Polaron formation in strongly correlated metal oxide system. We have been pursuing this work for some time. Polaron, I'll make a brief comment, then I'll of course define it in more detail. Polaron is interaction between electron and phonons. So this includes both fermion and boson. The interaction between them makes Polaron formation, and how it does and how we calculate, that will be the purpose of today's talk. Before I start my scientific description, a quick overview of my university, UT Arlington. Just few numbers here. We have more than 48,000 on-campus students. If we add the online students, it will be well around 60,000, but those students don't come to the campus regularly. The UTA is a R1 Carnegie Research University and is also a Texas Tier 1 university. The whole university, we have now, this is an old slide, we have now more than 1,600 faculties and 2,500 plus staff that include research staff and the office staff. Now the UTA is hiring about 100 new faculties this year and next year together combined, and this effort is going on right now. And we have about 20 fellows of National Academy of Inventors and several more of National Academy of Sciences and Engineering. The physics department, just a quick, where I work, we have now, as of last week, we have 30 faculty, 27 tenure track, and 3 professor of instruction. We are hiring 4 more this year, so next year this number will increase. We have about 150 undergraduate physics majors and about 80 graduate students. We have only few master's students. We usually don't want to admit master's students because the department doesn't want to give them assistantship. We mainly hire PhD or admit PhD students with full assistantship. We have about 20 researchers and senior researchers and postdoc, and definitely we'll have technical staffs and clerical staff. So that's a quick overview of the place I work. Now let's come to the talk. This work was started with a collaboration of Professor Wolfgang Jagermann, this gentleman over here on the left side. He retired 6 months ago in Germany, Darmstadt University, and the collaboration with Professor Frank Osterloh at UC Davis, that's still going on. So both two gentlemen are experimentalists, and I do computation and theory, hence the collaboration is mainly a complementary effort. The students who worked on this particular Polaron project, it started with Cedric Mayfield. He graduated, I think, in 2015. Then Horipodo joined my group. He carried on the Polaron work. Horipodo at this time is a postdoc at the Stanford University. And this is a new graduate student, joined my group last year. He came from UC Berkeley. His undergrad was from UC Berkeley. He is now carrying the Polaron work. All right, so this is a brief outline of what I'm going to do. Let me see if I have timing here, nice. So we'll start with simple introduction, then the methodology. The material of interest for today's talk is bismuth vanadate, and then we'll discuss how Polaron can be formed in bismuth vanadate. And then for some applications, we do need to suppress Polaron formation, and we kind of have a prescription how to do that thing and make few concluding remarks. A formal introduction. I don't think I need to emphasize why materials are important. The human civilization is named after the materials that people use. A few names like Stone Age, Bronze Age, Iron Age, then we can say it's semiconductor age, mostly silicon, or you can also call it a plastic age, that the time we are now living. And understanding the fundamental interactions in materials leads to technological advances, and also it will lead us to discovering new materials for applications in new technologies. So we work to understand the properties of materials from their fundamental electron-electron point of view, or electron-phonon, be it magnon or phonon or other interactions, and also the isotope effect within the materials. Now, one of the issues that is close to my heart is the climate change. Why it is close to my heart? Because I am from Bangladesh, and I'm still a Bangladeshi. And we know that because of the low-lying land in Bangladesh, it is New York Times predicted almost 15 years ago that by 2050, if the global warming, the way it's going on right now, or at the time, if we cannot curb it, the 80% of land in Bangladesh may be underwater. And that is not a very pretty picture. So part of that motivated me to go to the National Renewable Energy Lab in USA. That's the only renewable energy lab run by federal government at USA. I worked there for 3 years before I joined to the university. Now, this is a plot which at its first look may not be alarming, but because from 1850 to around 2025, projected at these few points at the end, the rise of global temperature is about 1 degree Celsius. So you can always ask, what's the deal of it? 1 degree Celsius. It's tiny. But mind it, this is the average temperature rise throughout the globe. And this is the problem. We have increased flooding. We have increased wildfires, frequent tornadoes, frequent droughts, and longer droughts. and larger cyclones, and of course, the polar ice cap melting. These are becoming too frequent. And I think the flooding, we don't need to tell flooding, the problem of flooding in Bangladesh. In California, I live in Texas, so it's far from California, but they have wildfire almost 6 months in a year, which is bad. I think I don't need to impress anyone. In Texas, we have problem with droughts. Less rain for months after months, which basically tells, without going into further details, that we need to somehow curb the global temperature rising or the global warming problem. One way is, of course, to stop burning fossil fuels. We can use renewable energy sources, like sources from solar, biomass, ocean, the wave energy, hydroelectric projects, wind, geothermal. We can use any one of those. But my interest, research interest, is on utilization of solar energy. One of the reasons is that it has a huge potential. If you think of the solar light or sunlight comes on the surface of Earth in an hour, and if we can convert it in an efficient manner, that 1 hour of solar energy can be converted into electricity that can power the whole Earth for about a year. So it has a huge potential. But the challenge is, again, we need a suitable and efficient materials to convert the sunlight into, let's say, electric energy, and then utilize it in a proper manner. So this is the key challenge. The key challenge is actually about the materials. So this is where my work comes in, working on materials that is efficient enough to absorb sunlight, convert it into, let's say, in electrical or chemical energy, and then utilize that into some practical way. I don't work on the utilization part. I think that's most of my engineering collaborators, they do on those parts. Now, for today, I will not talk about photovoltaics. We have worked a lot on photovoltaics, but for today, we'll talk about the photoelectrochemical splitting of water to produce hydrogen. So we can break water molecule, and if we get hydrogen out of it, we can use hydrogen as a fuel to drive car, or wherever you can use gasoline, you can use hydrogen fuel. But of course, the technology how we be utilizing is not combustion engine. It's a different technology. It's called the fuel cell. I will not talk about fuel cell. So the basic mechanism, what happens, if I have a semiconductor defined by its band gap, we have a valence band occupied with all electrons and conduction band unoccupied energy levels. And then if we shine light, then electron from the valence band excited to the conduction band, leaving behind a hole. And if this has an interface with aqueous solution, then hole can get into that aqueous solution. And if it has enough energy to go above the oxygen reduction potential, then it will make oxygen out of the water molecule. And then the electron that was on the conduction band, again, if this energy is lower than the conduction band age, electron can come here in water, and then due to the enough kinetic energy, or reaction kinetics rather, it can make the hydrogen. We need to have a mechanism to separate hydrogen and oxygen. If they mix, there will be a violent energy burst. We don't like that. And there are mechanisms how to separate them by some polymer membrane. So now if we use bismuth vanadate, that's the material of interest for today. Bismuth vanadate has a band gap of about 2.4 electron volt. It is one of the most popular materials in the last 20 or 25 years. And if you count paper, meaning search in Google or Scopus or any website or database where they count papers with keywords, you will see there are more than 25,000 papers on bismuth vanadate, and for different aspects. It's a very popular material. My first paper on bismuth vanadate that was published in 2009, I think by now it has almost about 900 citations. That shows how popular the material is. But one problem with this material is the hydrogen reduction potential is not below the conduction band. It just touches the conduction band minimum. Hence, this reaction kinetics has problem. This part is okay because you see that gap is larger from valence band maxima to the oxygen reduction potential. Now, to have an efficient, we call it photoelectrocatalyst, these properties needs to be met. It has to be a stable semiconductor in aqueous solution. Most metal oxides are, not all. The band gap has to be within 1.7 to 2.2 electron volt. It must have right band edge position. These are the conduction band edge, this is the valence band edge. The position of them should straddle these reduction potentials. Bismuth vanadate has trouble with this potential. And then, of course, it has to absorb light efficiently. And then once it absorbs light, the electron or hole, they have to travel through the bulk of the material, since the transport has to be good enough. For today's topic, we are actually working on the transport. We have worked throughout all those other properties. We find a mechanism how we can predict a good, let's say, stable materials, or how to engineer the band gaps, how to engineer the band edges. Our group, or rather my group, this is what we do. And anyway, so the bismuth vanadate, it has, of course, different phases, the polymorphs. The one that is stable at ambient condition is this monoclinic structure. So all the calculations or computation we will show will be based on these crystal structures, which has a space group of C2C. Now, how do we calculate this? So we use first principle quantum mechanical approaches. It's a many-body problem. And for first principle approaches, the two most popular route is, one route is wave function based method, which is a Hartree-Fock based method. If I have n electron, it will have 3n degrees of freedom. Another is density functional approach. The density functional approach, all it says that if I know the ground state electron density, that will be enough to predict all the ground state properties of that system. That was proposed or published by Hohenberg and Kohn in 1963. After a year or two, Kohn, when he returned to California in Santa Barbara, with his postdoc, they published a practical way of computing those properties. That's called Kohn-Sham methodology. And for that, Walter Kohn received Nobel Prize in 1999. So this is a heavy, impactful method. Hartree-Fock, probably most of you know that. This is also a very impactful method. But we choose to work on this one. One of the reasons that it's only electron density. Density is a scalar function. It depends on the position of the wave function or n electron system. So it essentially has 3 degrees of freedom. It's more accessible, computationally less expensive than the Hartree-Fock method. Now let's talk, what do we mean by Polaron? It's a typical material, iron oxide, which is a hematite, the alpha phase of iron oxide. This is basically the rust. If you see, if you throw an iron bar outside, especially in humid climate in Bangladesh, you'll see rust is this reddish rust on the iron. That's alpha Fe2O3. Now, this is an excellent insulating materials. It has a technical name. It's called charge transfer type Mott insulators. Now, for the first one, if we think just the electron distribution, the blue atoms or clouds are the iron atoms, the red one are the oxygen. See, if you think of, because oxygen are more electronegative than the metal atoms, so oxygen took or take electron from the metal atoms, so metal atoms become relatively positively charged or less, they have less electrons. And if I distribute those less electron cloud in simple band electron approach, they will be distributed over all the metal atoms uniformly. But then, if conditions is favorable, then those extra electrons or lack of electrons, we can also call holes, they can collapse into one site. If that happens, then this gathering of these extra charges, that's we call Polaron. In terms of energy surfaces, if we think of band electrons, we can get a parabolic type of potential well. And then if those electrons try to travel and then stuck somewhere, and if this lowers the energy, like the red one, then of course the electron which was originally at the top of this energy surface it will come to that lower energy surface if we can make it. So that's how the polaron is formed. Now let's have a more detailed look. Think of this hypothetical square lattice, where how much time I spend. Okay. In this hypothetical square lattice, these blue atoms are the metal atoms, red one are the oxygen. If there is an extra electron, we supply it in here, the electron will most likely try to go to the positively charged metal atom, and because the electron is negative, it will create a local lattice distortion. And this local lattice distortion, if it's lower the energy surface or energy, then the electron will be stuck in there because there's lower energy state. That will create the polaron. If you look at the density of states, before the electron gets stuck, the band kind of electrons, the density of states for valence band and conduction band will have a clean gap. But once the electron is stuck, there will be that extra defect level show up in between the band gap. That's the Polaron state. By the nature of Polaron, we usually consider two types of Polaron, and the naming is extraordinarily innovative. If they're smaller than the lattice constant, we call it a small Polaron. If they're larger than the lattices, we call them large Polaron. So basically very naive naming. And then two Polaron, when the Polaron state forms, all the metal atoms will show this kind of periodic potential at the metal atom's site. So electron can jump from one side to another, provided it can overcome this energy barrier. Some numbers that will probably give some idea of what Polaron does in terms of diffusion lengths. If you think of silicon, the diffusion length is in average 100 to 200 micrometer. If you think of iron oxide, not iron, tungsten oxide, tungsten has a 5D electrons, so not very localized. Then its diffusion length drops 3 orders of magnitude, around 400 nanometer. Bismuth vanadate, the one we will be talking, I have to be quick now, is about 75 nanometers. Again, an order of magnitude less. Iron oxide, the one that I showed, which is basically rust, it is just 2 to 4 nanometer. Now, these numbers were taken from these two papers. These two papers, they are from the same group. It's Ned Lewis group from Caltech. And I selected these numbers because they measure the diffusion lengths by this almost similar technique. So these numbers can be compared with each other. So that tells us that we know polaron is formed in bismuth vanadate. We know strong polaron form in iron oxide. Their diffusion length is extremely small, the charge diffusion length. That tells how bad conduction in those two materials. Now, two other examples. Now, I choose to show it because the first student, Cedric, he started working or calculating polaron on titanium dioxide. These are experimental behavior. For anatase, if we increase temperature, resistivity increases. It's a normal behavior. For the rutile phase, and these are the crystal structures for these two phases, as the temperature increases, resistivity shows a declining trend. So this is a typical feature of polaron formation. With temperature increases, it gets more thermal energy, and it has the tendency to jump over the barrier, the polaron barrier. Now, one thing I must point out, even though the resistance or resistivity is decreasing with respect to temperature, but if we look at the scale, the resistivity where the polaron forms, this y-axis, this is in ohm centimeter, this is in 10 to the power minus 4 ohm centimeter. So where polaron do not form, the overall resistivity is usually much lower than the phases where polaron forms. Now these are the two banded structures. This is a quick thing just to show the behavior. This is a typical band conduction in zinc oxide. This is the zinc S contribution, hence it's almost like a parabola. These are these electrons that comes to the conduction band. They can move with a very low effective mass. This is the banded structures of hematite or iron oxide. The conduction band is flat. If we calculate the electron effective mass, that will give you almost infinity. So once electron excited to the conduction band, electron literally stuck in there, don't want to move at all. I calculated this thing many, 8-9 years ago, that how much pressure I can give on iron oxide to make the band more conductive. And the answer was 60 gigapascal. And then I started looking where I can get 60 gigapascal. You can do, of course, diamond unveil experiment, which are very expensive ones, or you can go to inside Jupiter, planet Jupiter. So if you drop a metal iron oxide, not metal, the rust iron oxide, inside the planet's atmosphere, the pressure is so high, it will behave like not a good conductor, but kind of conductors. These are fun things to check. Now, these are few theories about Polaron. I would not explain these formulas. These are all textbook stuff. Just a history. I put these things for history purpose. As you can see, the Landau in 1933, he first talked about electron being trapped in a lattice site. He did not coin the word Polaron. It was just 1.5-page paper, but that is now considered to be the first paper where the concept of Polaron was discussed. But then Landau also worked with Pecker from 1946 to 50s, and they have few publications. And you can see the first one, that their model, this Landau Pecker model, it's basically classical electrodynamics. Nothing more mysterious than here. Then Froelich, for large Polaron, he wrote this Hamiltonian, and during the time of 50s and 60s, quantum electrodynamics was forming. So these kind of model Hamiltonians are getting more and more popular. Many people worked on this kind of thing, including all the big names you can think of. So Froelich, he modeled the Hamiltonian, which later found appropriate for large Polaron. Polarons are large enough, are larger than the unit cell of a crystal. And then around 1959 or 60, Holstein and Emin, there is another guy, Emin contributed later. They write an Hamiltonian, which is more appropriate for a small Polaron. Small Polarons have much slower conductivity, lower conductivity than the large Polaron. Now, these are the few things about bismuth oxide, bismuth vanadium oxide. The lattice constants, we check the lattice constant and then compared it with experimental values. They make sense, at least within some small bar of errors. I will not delve on that thing. I will spend few seconds on this slide. This is the band structure for bismuth vanadate. And the conduction band minima is somewhere in here. As you can see, CBM is written. VBM is on here. Now, if I see this thing, they are not at the same momentum value, the crystal momentum value. This kind of thing that will need a phonon-assisted electron excitation. This we call indirect band gap. And this is the density of states. Now, when we plot density of states, projected density of states for different atom and their orbitals, when we see the valence band density, conduction band density of states, the vanadium 3D has a sharp contribution. That already tells us that Polaron can be stabilized, at least electron Polaron can be stabilized in this material. Then this is how we stabilize Polaron computationally. So if we have a unit cell, this is not a unit cell, it's a supercell, larger than the unit cell, then we can add electron or hole. Adding hole means take out one electron, and then you do full relaxation by some computational method, structure relaxation, atomic position relaxation. Then finally, we may see that these electron or hole, they will localize. Electron will localize at the metal atom, and the hole will localize at the anions, oxygen atom. And this is the basic technique of stabilizing Polaron computationally. Just DFT would not do it. We need to use DFT plus U Hamiltonian or DF density functional perturbation theory to do this work. Now, first we tested the Polaron formation at the vanadium site. We add an electron, relax it, and we have seen that electron get trapped at the vanadium site And because electron get trapped, the vanadium, the oxidation state changes from 5 plus to 4 plus. And these are the lattice distortion due to the localization of electron. And this too tells us one signature, the lattice distortion and electron get trapped. This is a signature of electron polaron. And then you can do the DOS plot to see if we see that defect states. We do see it. This is a clean bismuth vanadate. And when we stabilize a polaron, we see that defect state or polaron state inside the band gap. Now, similarly, we did explore whole polaron formation. So, whole polaron can form on the oxygen side. This is what we tested. On the oxygen side, we will check the oxygen oxidation state within the computation. Oxidation state changes for the oxygen where the hole is stabilized, and also the lattice, not the bond length distortion, is what we expect. And so we also do the DOS plot, density of state plots, and this is where the polaron signature comes in between the band gap. Then also, of course, we can stabilize hole on bismuth side, which we did, but this is what we see, this spherically symmetric charge density around the bismuth atom. That tells us that bismuth s orbital stabilize that hole, and s orbitals are always delocalized. So this is not a localized polaron trappings. It cannot act as a polaron. But on the other hand, because electron is trapped in a s delocalized s orbitals, the bond distortion shows some effect to confirm electron is trapped in there. So we calculated the polaron binding energy by simple common sense way. And we see that whole binding energy is about 0.0055 electron volt. Oh, sorry, this is the whole, it's a comparison of whole binding energy on the bismuth side and oxygen side. Because we did stabilize a whole polaron on those two sides. And from these two, we can see that whole polaron on the oxygen side is more stable than on the bismuth side, which is supposed to be. Because on bismuth side, it was stabilized on bismuth 6s orbital. 6s or any s orbitals are very delocalized orbital. Hence, stabilization of polaron on s orbital will never be strong enough. So these are just sanity checks. Now, we plotted where is what. So this is our theoretical energy levels. We calculate the whole electron polaron, which is situated about 0.38 electron volt below the conduction band. And the whole polaron is situated about 0.8 eV above the valence band. And then another one, is, which is the bismuth one, is too close to the valence band. So it's basically a shallow defect level, so it cannot be a polaron. Now, this is the experimental numbers. Now, these experimental numbers these are measured by my collaborator in Germany, Professor Wolfgang Jagermann. And this, the data they provided us. And if we look at the numbers, we actually predicted these levels too close than I was even expecting. So Jagermann, he invited me to give a seminar in his department in Darmstadt University, which is 30 miles south of Frankfurt. So when I was presenting my numbers, I saw some of the students and Professor Jagermann get excited. And then they showed these numbers. They did not publish those numbers by that time. Then I sit down and check those numbers. They're really very close. So that tells, at least to me, that the methodology or the techniques we have worked on or try to make the procedure is good enough to predict properties for even a strongly correlated system. Some of you who worked on density functional theory, there is a criticism for the density functional theory is not a good one if you want to work with a strongly correlated system. True, but then any mathematical methods or computational methods, we need to spend some time to find a right strategy. to get the results out. Now, of course, recently, what we have done, we also stabilize whole Polaron on bismuth oxygen polyhedra, and that seems like more promising than stabilizing whole Polaron on the oxygen side. Now, that result is not published yet, so I did not put it on the slide. One of the consequences of this Polaron state is the effective band gap is reduced by these Polaron levels. The effective band gap was 2.4 electron volt for bismuth vanadate. Now, this band gap is now less than 1.4 electron volt. That 1.4 electron volt is not good for water splitting process. Now, we did calculate the Polaron excuse me, conductivity. So if there are two possible sites, then the electron Polaron is now sitting at a vanadium site. Then if we supply energy, it could be by heat energy, then it can go through the energy barrier and hop to the other side. This hopping, by modeling or simulating this hopping, we calculated this energy barrier, and which is also known as activation energy. And then we plotted activation energy for both electron Polaron on vanadium side and whole Polaron on the oxygen side. And we see that for whole Polaron, activation energy is less, meaning the whole Polaron conductivity in bismuth vanadate will dominate over the electron Polaron conductivity. And that was experimentally confirmed fact. Bismuth vanadate shows mainly whole Polaron conductivity. And then we use some form of diffusion equation and their parametric representation to calculate the mobility. We need for that the nu zero. For nu zero, we have to calculate this phonon dispersion plot and get the phonon and calculate these numbers. And here also, as expected, the whole Polaron has higher mobility than the electron Polaron. Just to compare it, if you see drift velocity of electron in silicon, this is 10 to the power 3 to 100 to 1000 centimeter square per volt per second, compared to these numbers, which have 10 to the power minus 6 or 8. So it's the whole Polaron or electron Polaron, they're always not very good. Now, Polaron in this this part, I'm already over 30 minutes. Just give me a few more minutes, I will finish it. So for whole Polaron, so far what we did is that we consider an electron comes and hole comes, it gets stuck in an atomic site, but did not mention the mechanism how those extra electron or hole can come. One of the way and the most possible way for any metal oxide, when you synthesize metal oxide, oxygen vacancy is very common. Oxygen vacancy can provide that extra electron or whole state. So this is what the thing is. If I make an oxygen vacancy in bismuth vanadate, then do the dot plot, and this is the defect state due to oxygen vacancy. This is the band structure. So this is partially occupied defect level. And that is the Polaron state in bismuth vanadate with oxygen vacancy. And oxygen vacancy formation in bismuth vanadate is well known. There are many experiments where people showed that you cannot avoid oxygen vacancy in bismuth vanadate when you synthesize it. So then the question is, because the conduction is very poor, and for photoelectric water splitting, we need a good conduction. Other than the conduction part, bismuth vanadate looks okay. So the question is, how do we suppress the Polaron? So this is another project. This is the project where we start working with Professor Frank Osterloh, who is a professor at UC Davis, University of California, Davis. He performed experiment to confirm our computations. So this is the Polaron state with oxygen vacancy. Then because we know that oxygen vacancy will provide the deficiency of 2 electron, rather excess of 2 electron, where the oxygen is absent. So if we put at some point near the vacancy site 2 calcium, then that can neutralize this defective state, which it did, and then you see that the band gap gets cleaner, no Polaron state. So if calcium can do it, can magnesium do it, can strontium do it? Because they are all on the same column. In principle, yes. But experimentally, my collaborator mentioned, calcium is the best. They can synthesize it at relative ease. So then we do further optical absorption calculation, and we have seen that with calcium on bismuth vanadate, when there is oxygen vacancy is involved, even the onset of the optical absorption is at a lower energy. So that not only neutralizes the defective state, or here rather Polaron state, also it improves on the optical absorption to excite electrons. If we see what calcium does, so before calcium doping, oxygen vacancy, we'll have this kind of Polaron state. Once the calcium doped strategically, then this density dispersed throughout the supercell. Another point, I think this is a more encouraging point to me at least, bismuth vanadate by itself, as we mentioned in the beginning, the lower part of the conduction band doesn't straddle the hydrogen reduction potential. Once the oxygen vacancy is in there, then that even gets worse, it gets down. But then if we add calcium to neutralize the defect level or Polaron level, the whole the conduction band rises in energy and clear this hydrogen redox potential for water splitting. So this not only reduce the Polaron state, so hence increasing conduction, but also increase the optical absorption, and it raises the conduction band high enough so that now it straddles the hydrogen reduction potential for water splitting. So it does several things. Some of the things we did not anticipate before these results came, but then when you see the whole picture, it was really very encouraging. I will skip this slide. Now these are a few points. The Polaron conduction fundamentally is different from band conduction. And Polaron is quasi-particle. It's a mix of, or a combination of a fermion and boson, electron and phonons. There is an electron-phonon coupling or interactions. And Polaron usually form in a strongly correlated polar system, resulting in slower charge transport. Effective band gap of the materials, because of the presence of Polaron state within the band gap, the effective band gap reduces. Hence, the overall water splitting can be affected. And also, we are still in search of a better mechanism to suppress Polaron states. Now, one point I think I need to mention here, which is not written here, is that the electron-phonon interactions, the true coupling between electron and phonon, is not calculated within this presentation, but those calculations, we have done it in the last few months. But if you search literature, those are not very, in terms of ab initio or first principle calculations, those are not very well established, so we have to find an innovative way to model those things. My recent new students, he's from, he did his undergrad in Berkeley. I show he is working on that thing. He's good, I think. Well, he sent me an email yesterday that he already calculated some of those things successfully. So that's all for me today. Thank you very much, and I appreciate your time.
It's going. Working. Can you hear me? Yes. Thank you, Dr. Huda, for such a wonderful talk. Questions for Dr. Huda? Looks like there is a band gap. You need some infusion of energy.
Okay.
Yeah.
So conversion of solar energy to electrical energy, the bismuth vanadate that you talked about, does it have any environmental adverse effect? Or the in general, does it really solve the problem, or do we still have something to worry about? We are destroying our environment. So,
You know that the most popular material for, at least for photovoltaics, is still silicon.
silicon, yeah.
Is still silicon. But silicon has an indirect band gap. So it's like the conduction band minima and the valence band maxima, they are not at the same crystal momentum. So that means when electron get excited, it goes up. That gap is around 3 electron volt, too high for a good photovoltaic. So we always need electron phonon coupling. That's actually a wastage of solar energy to get the photovoltaic whatever we get right now. And silicon has a big limitations. The lab efficiency for a single crystal high quality silicon, I think nowadays is about 24-25%. The single junction solar cell from the thermodynamic limit is no greater than 32%, about 32%. Bismuth vanadate has a too high gap, it's 2.4 electron volt. But so it is not used for photovoltaics. It is used for solar energy conversion to the chemical energy. So it breaks water molecule and create hydrogen out of water molecule, and the energy is stored in hydrogen bond. But still, it doesn't solve the problem. And that's why these are ongoing problem. We get funding from Department of Energy in USA. It's a few years ago, the program officer, a lady at the time, when I was presenting my report to the committee, she asked me, Mohammad, when do you think you can give us a good materials that will really work? I said never. He said, why? Then he will stop my funding.
That's a wonderful answer. Further questions to Dr. Huda?
Yes.
You said that if we increase the temperature, the resistivity of a polaron decreases, right?
Yes.
Is the mechanism behind this is same as semiconductors?
No. Because in semiconductor, once the electron is in the conduction band, if you increase temperature, the resistivity increases. But in polaron, if you increase temperature, resistivity decreases. But the catch is, material which form polarons, their resistivity is already too high. So even it decreases, let me go to the slide, probably that one of the this one. Yeah. So as you can see here, this one, right? Oh, I cannot see my cursor. Probably I have to do this one. That's fine. Can it go there? Yes. The resistivity decreases with temperature, right? But if you see the y-axis, the resistivity is in the unit of ohm centimeter. Where polaron doesn't form the anatase polymorph of titanium dioxide, the resistivity increases, but the resistivity is in the unit of 10 to the power minus 4 ohm centimeter. So even though it's increasing, let's say up to 300 Kelvin, about room temperature, still its resistivity is lower where polaron forms. Now, why its mechanism is different, let me go. It's here. Its mechanism is different because, the polaron, I think not this one. This is better. Let's say that electron is stuck or hole is stuck in one of those lowest energy surface, right? Then to to move, it should jump from one atom to the other. To do that, it has to overcome this energy barrier. If I supply heat energy in terms of increasing temperature, it can provide enough energy to go above the barrier. Of course, sometimes this phenomenon like quantum tunneling happens, but that's random. That's not, I cannot rely on it. So if I supply enough energy, the probability of electron jumping the barrier is much higher. So that's why at higher temperature, resistivity shows a declining trend.
There is another questions from there. One other question from
Yeah, I have I have a technical question. So, when you calculate the Polaron binding energy, how you calculate the number of Polarons, like that N?
Let's go to that binding energy formula. Where is it?
I think.
This
Yeah,
one, right?
yeah, this one.
So N is the total number of electrons
Okay.
in the supercell, wherever you are taking it. So when we do electron polaron, we add extra electron to the N, right?
Yes.
So it's N plus 1, that's the electron polaron. When we form a whole polaron, we take one electron out. So that's N minus 1 electron. So these two differences here, as you can see, the first term is when the polaron is stabilized. The second term, when there is one extra or one less electron, but polaron is not stabilized at any atomic site. It's
Yes.
kind of band distribution over all the cell.
Yes.
So it's distributed over all the cell versus polaron is formed. That difference, energy difference, will give us an idea of polaron binding energy. Now, these are always an idea. You can always calculate binding energies in different way.
Yes. Okay. Thank you.
Thank you.
Any further questions? If not, let's give Dr. Huda a hand.
Thank you very much.
Yeah, assume there is no further questions. Thank you, Dr. Huda, for this wonderful talk. The next talk is by one of the hosts, Professor Mohammad Kamrul Hassan. He is going to tell us, the title of the talk is Journey Through Time to Understand the Birth of Bose-Einstein Statistics, following Bose's own path and others.
Hello. So, good morning, everybody. I'm not supposed to give a talk, but there are some gaps to fill up, and I'm also requested by my colleagues and organizers to give a talk about actually, not a talk. Since the theme of this conference is on Bose-Einstein statistics, and since I have something to say, and being an organizer, I think, okay, it's not a bad idea to talk. So basically, I want to talk on the historical perspective of Bose-Einstein statistics, how it was born, and the contributions by other people. I'll try to cover those. This is Karjan Hall. I'm sure everybody in this audience have seen it. And this is the place where quantum statistics was born exactly 100 years ago. The reason I feel always the obligation that Dhaka University failed to let the world know such a milestone discovery, such a breakthrough, that what everyone in Germany and Europe and everywhere else, all the giant physicists were trying to do, someone sitting at Dhaka University at Karjan Hall did that all alone. We failed to tell our students that it is possible to do research in an environment that is conducive, not conducive to research, challenging environment. Our students need to know that. It is possible to do research, breakthrough research in this soil. And this is why I've always talked about Satyen Bose. While I was teaching, I realized that there is not a single statistical mechanics book where Bose-Einstein statistics was introduced and mentioned about his original paper and mentioned about how he did it. The way it is now in the statistical mechanics book is not the one Bose did. I find the way Bose did should be included in the textbook so that you can see the contrast. Why he realized when he was teaching the Planck's radiation law, what are the flaws that he realized that need to be corrected. Everyone should know it. And when the idea was born, everything should be, the whole thing should be put in the perspective. So I think in this perspective, we have an obligation to rewrite the statistical mechanics when we introduce the Bose-Einstein statistics. I'll try to make a brief journey and discuss what are the logical flaws that Bose identified. Some of the aspect has been mentioned by Partho Ghosh. We are lucky to have him here. What was the Bose's reasoning for using the factor 2? He explained that that is not mentioned in any statistical mechanics book. It should be included. Why is the historical context of black body radiation rarely discussed in the textbook? Could Einstein have collaborated with Bose to extend the Bose's work from the photon to an ideal gas, leading to the prediction of phase transition, which we know now as a Bose-Einstein condensation? Of course, Einstein is no more alive, so we cannot know his answer. But when I talk about Bose-Einstein statistics, when I read about this, these are the questions that come to cross my mind. I cannot just ignore them. The second part I will not talk actually. I will remain within this. So, generally we know that any hot object, it radiates. And the intensity, radiation depends on the temperature of the object. And one might expect also it depends on the nature of surface, but it is not. black body radiation idea was first born by the concept proposed by Gustav Kirchhoff in 1859. And he himself said, the graph that you see, the spectrum experimentally was known. If you see, as we increase the temperature, two things happens. The peak, where the intensity is maxima, shift towards left, towards lower wavelength. This is one thing. How does it shift? Where the maxima occur, the value of the wavelength times the temperature, these two are locked. They remain constant. The way it shifts, that their product is constant. This is one thing. And as you increase the temperature, the area under the curves increases as the fourth power of temperature. So these are the things that experimentally was known then. But the onus on the scientist at that time was to find the reason behind, the theory behind. That was missing. So journey began from there. So Gustav Kirchhoff himself said that emissivity must depends on only the frequency vis-a-vis the wavelength and the temperature. Rightly so. And then he also said, most urgent open problem in theory, this is the most urgent theoretical problem in theoretical physics. Then in 1893, Wilhelm Wien gave a formula, and he renewed that formula by giving even better formula by saying that it depends on nu cube times e to the power minus alpha nu by t. And he got the Nobel Prize for that. And that formula was fine for certain regime, but not for the entire spectrum. So journey did not stop there. So from there, 65 years long journey started. The first successful theory was given by Rayleigh-Jeans. They're British. They assumed that they took a container, cubic, and said that electromagnetic radiation is a reflector, so perfect reflector, so they produce standing waves. And we know that since the length is fixed, wavelength and standing waves is produced, the formula is given here, A sine kxx. So 2n must be node. If you impose that restriction, then you find kx times L must be equal to nx pi. But so textbook problem you have all seen. So you see that the modes, the k is quantized, the number discrete value. This is because just confinement of the electromagnetic radiation within a cube. So they found the density of states. But this is of the wall, atoms in the wall. So they found exact value 8 pi nu square by c cube. So they took, in the K space, they took a shell or sphere of thickness dk and found the volume, and just converted using the k equal to 2 pi nu by c. The density of states is found to be 8 pi nu square by c cubed. Of course, the factor 2 here is the one that Einstein also mentioned due to the polarization in two direction. So that 8 pi nu square by c cube factor is quite historical because everybody wanted to find that out, which we will know later soon. And then, once he found the density of modes, all you need to find the energy. So they assume the equipartition theorem for potential energy and kinetic energy, the average energy for each contributes to half kT, so you have total kT, so you just multiply. That formula too is okay, but not, it works fine on the other end of the spectrum. So we have two formula. One is Wilhelm Wien's formula, which work in one extreme of the spectrum, and we have Rayleigh's, which works in the other extreme. For the higher wavelength, fine, but lower wavelength, we call it ultraviolet catastrophe. It doesn't work there. So, still it is all about classical. So here, Planck's entered. By the turn of 19th century, a rivalry between two groups of theoreticians was surfacing. One school of physicists believed energy flows continuously between radiation and materials, so in themselves unbroken and incontinuous. That was about one school of scientists. On the other hand, the rival school of theoreticians considered matters were not continuous. Rather, they are composed of discrete atoms or molecules. Thermodynamic properties of such materials could be calculated by studying the motion of these atoms and molecules. So thermodynamics is all about macroscopic properties. So that at that time, a school of theoreticians, they were trying to say that atoms, discrete, by studying the atoms inside the material, you can understand the thermodynamic properties. So Planck was famous for thermodynamics. He did his PhD on second law of thermodynamics. So he was famous. When he saw this rivalry, he decided to stay away from this. He wanted to pick up something that is neutral. So in 1897, Planck picked the black body radiation problem as a neutral area of research. In 1900, a famous experimentalist, Heinrich Rubens, visited Planck because he was invited by Planck to have a dinner with him. During the dinner, Rubens told about the result he obtained. They studied the cavity radiation even at a very low frequency and told him that the existing theory did not agree with their experimental results. So after Rubens left, Planck continued to work on his own, all alone. So he worked whole night and he found the formula. He wrote that formula in a postcard sent back to Rubens, asking him to see if that formula works. Following day, he received reply from Rubens telling that perfect. That is the magical formula they have been looking for. So that was this formula which our Bose was teaching at Dhaka University while he was teaching this formula, he realized some flaws. What were those flaws? Bose was teaching thermodynamics and Maxwell's theory of electromagnetism. It was exactly during this time he acutely felt the lack of logically satisfactory derivation of Planck's law. This 8 pi nu square by c cube, how did they derive? It's a classical formula theory they derived. So using electromagnetic radiation. And the h nu by over e to the power a beta in the denominator, you see the other factor, they assume energy is quantized. In some sense, it's quantum. But at the same time, what was it? It is the radiation and the wall atom, their exchange of energy is quantized, not the photon itself quantized. The idea of photon was not there, totally absent. So there were a flaw in both sides for both the factors. He was not happy with that. So this is the time he started to work on that. So what he did is that he assumed that by this time photoelectric effect was already out, and he knew that photon has moment h nu by c. So these are the things that he used. So what he did then, he assumed that energy equal to n times h nu. So there are n number of photons of s types, and each of them had frequency nu s. So he measured the phase space, the volume of the phase space. Only the shell of dp. So you have a sphere, football, the thickness of the skin of the football, say dp. So volume of that shell is 4 pi p square dp. And since it is a phase space, so he also multiplied by dx, dy, dz. And then he realized that dx, dpx is greater than or equal to h, dy, dpy. So you see, the uncertainty principle is somehow, in some sense, is there. So in the phase space, you get the h cube. That is the minimum volume in the phase space, that you can divide the whole phase space into a cell of the elementary volume h cube. That is the magical realization that he did. So he found the volume of the phase space, and then he divided the total volume by h cube, and he found the number of cell, meaning the state. Then another story that Professor Partha Ghosh mentioned, there was a mismatch of factor. So that was 4 pi nu square by c cube, but the extra factor you have to multiply to get the correct answer for that counting. But 8 pi nu square by c cube was also found by Rayleigh-Jeans, but with using different, not quantum mechanically. But this time, this is quantum mechanically. So Bose was extremely happy to be able to derive this factor quantum mechanically, and Einstein liked it very much. So he assumed the total number of cell, small volume of each of them has a volume h cube, he assumed that it is equal to as of s type, which is 8 pi nu square by c cube. And then, so as is the number. And then he assumed total, out of the as number of cell, he assumed that there are p naught number of cell which has no photon. There are P1 number of cells which has only one photon. There are P2 number of cells which has 2 photons in each. So that means he was counting the cells. And here comes the indistinguishability. So he found the expression for the number of ways that S number of cell, how many ways we can distribute them. This was not done ever before. So here comes the indistinguishability, statistics, and quantum mechanics. Everything came here. So he just, and then he assumed that since there are, say, R number of cells, if you sum them up, you get the total number of cells. You get the formula also for the energy. There are S types. So you have the product sum also. What you do then? You maximize it. Number of equilibrium state is always the one that corresponds to maximum entropy. So you take log on both sides, you get the entropy, and then you maximize it. This is exactly what he did. I don't know why our statistical mechanics book does not treat in this way. Instead, the way you see in the textbook is Ni number of photon, in the Gi number of cell, how many ways you can arrange them. That is how we are taught. Not the way like product sum of this As and P naught to the power P naught, P1, and their factorial. Why did we divide? Because if you interchange the cell among P naught or among P1, they are indistinguishable. That's why you divide. So if you maximize it, just a little bit of calculation, if you apply Lagrange multiplier, you get this formula. I find his derivation is excellent, but not a single textbook we find. So later, when it was sent to Einstein, he immediately saw the minus in the denominator. So there is a chance of getting singularity, which is a signature of phase transition. And that's why he realized that if we can apply it to the ideal gas, there is a possibility. Einstein applied that, but he did not work with Shyot Bose. It is always expected. If you get the idea from someone, you do that collaboration. You work with the person. But at the same time, Shyot Bose was grateful to him because if it was not Einstein, his paper, it would not be published and we would not know anything about Shyot Bose. So that is in one hand, I think in my view, Einstein did not do the right thing. On the other hand, if Einstein, what he did, if he did not do that, we would not know Shyot Bose the way we know now. So Shyot Bose, rightly so, he was very grateful to him. But had Einstein worked with Shyot Bose, perhaps they would together would do a lot of other works. And also, Einstein invited him, but not to work with him. He invited him to go to Europe, meet all the other scientists like Marie Curie and other scientists, they are the then scientists. But only concern is that things could have been different had Einstein worked with Satyam Bose. So then later on, perhaps he would have PhD and other things. Satyam Bose never had a PhD. And for that, Dhaka University was reluctant to promote him as a professor. When the advertisement was made, Dr. Devendra Mohan Bosu was also applied for the same post. And the applications were sent to Summerfield. Summerfield suggested that Devendra Mohan Bosu should be promoted given that post, because Devendra Mohan had a PhD from Cambridge and he had a postdoc in Germany, so he had a better number of publication and degree, so he was offered, but Devendra Mohan did not accept that. Meanwhile, Satyam Bose requested Einstein to write a recommendation letter for him. When he requested Einstein, and then he asked, why do you need recommendation letter? They said, I have applied to Dhaka University for professor position. So why do you need recommendation? Because I don't have PhD. Then he said, is there nobody who understands your last paper? Okay. He reluctantly, he wrote a recommendation letter, but he was surprised that his last paper was not recognized enough. That he had to write a recommendation letter to recommend Satyam Bose to become a professor. So, these are the stories we should all know. Anyway, thank you for your patience and thank you for giving me opportunity to
Questions?
It's not really a question. I have maybe a story to share. So I had the opportunity to speak to Professor Freeman Dyson a few years before he passed away. He also didn't have a PhD, and but he was a professor at IAS. He told me something interesting that is not known in the popular media. And I think it has some bearing on this topic. The story he told me was about the relationship between Ramanujan and Hardy. So according to Freeman, and I have the recording, by the way, I haven't released it yet, it's on video. Hardy knew what was wrong with Ramanujan. He knew he could have taken Ramanujan to a tropical medicine doctor early on, and that would have solved the problem for Ramanujan. But according to Freeman, Hardy was a playboy. All he cared about when he was younger was cricket, and later on, snooker. And he just didn't bother. And it's not Hardy who took Ramanujan to Cambridge, it was Powell. But Powell died in the First World War, and Hardy inherited Ramanujan. He, of course, credit should be given to Hardy for training Ramanujan and working with him and all that. But I think there's a theme here, and the theme has to do with colonialism and how, we are products of our time. We are not, here from our perspective, we are judging these people for why. But, at the end of the day, there is reference in Einstein diary to how he he held racist, views about Chinese women, for example. But at the same time, Einstein also helped the black people of Princeton. So I'm not trying to say Einstein was a bad person, but he was a product of his time, right? So I think, we need to look at that in those sort of, and there's also Ray Chaudhuri, right? Ray Chaudhuri got his PhD because he applied for it. He didn't really have a PhD. He didn't go through the PhD. He used his work and applied for a PhD. And John Wheeler wrote a very glowing recommendation on the PhD report. So I think we need to understand. We need to have a decolonized version of our history. There needs to be. Decolonization is a fashionable field, but the problem is that physicists, I'm rambling, physicists don't tend to appreciate these ideas which are there in the social sciences. But I think that we need a decolonization of the history of physics.
That's a very
Bravo, Kipro.
insightful comment.
When I was watching the movie on Ramanujan, exactly the same thought, but I didn't know that it was not Hardy who invited. Thank you very much for that. And I also thought that Hardy didn't do the right thing. Had he did, we would have Ramanujan live longer, perhaps. So, yes, and the same thing goes with Einstein and Bose. Whether we like it or not, it matters. I crossed my mind. I question myself. I ask always that why Einstein invited to Europe not to work with him, just to walk around, wander around, go to the lab. He was not an experimentalist at that time. He was a pure mathematician, a theoretician.
Hello.
So, yeah.
You are overtaking the tea time, of course. It's already late, it's tea time.
Okay,
But one thing I want to mention that what I read about Ramanujan and Hardy. Hardy recommended Ramanujan for the Royal Society Fellowship. He has strongly recommended. This should we recognize that. He was opposed. All the academy fellows opposed this fellowship, but Hardy pushed it very hard, and he got the Royal Society Fellowship, FRS, he was.
If I may intervene, I think, there is no contradiction with what Tibra Ali said, what you are saying. This can happen in the same, with the same. He of course took Ramanujan as his project. That's not unheard of. That's very common, and he pushed Ramanujan that way. But even in that movie, if you see that Ramanujan was hurt, and his face was showing bruises. And at some point, Hardy was asking what's wrong, and he said, "Did you ever even look at me and look at my face?" So this is again the very English culture to some extent.
The main reason it is already. The story is all around here. Ramanujan was a vegetarian, so he cannot survive the hard winter. So he has to cook his own meal, and he has a tuberculosis. So it was the reason for her death, or his death.
No, absolutely. Nobody is blaming Hardy for the tuberculosis.
Ramanujan did not die of tuberculosis.
Okay, thank you.
He did not die of tuberculosis.
I would like to make one quick comment.
Yes, please, Dr. Huda. Yes.
Yes. I think the part of our discussion in this last few days, and also Professor Kamrul Hassan mentioned, that the story how Shotten Bose developed the theory isn't being told even now. Yes, that's true, but we can change it. I think the easiest way to change it, American Institute of Physics, they have a pedagogical journal. This is very popular, American Journal in Physics. And people write pedagogical article in there. We can write a pedagogical article, how Bose derived the theory, and it will be published. That journal is for the physics teachers. And I'll be happy to help in writing this thing if.
Yes, wonderful. So I think we made some good progress. Yeah, let's thank the speaker and who is the secretary of this whole thing that is happening here again. And let's all join for tea downstairs.